recording on. Somebody might ask me at the beginning of classes, you know, hey, did you remember to start recording? Because sometimes I forget. But I'm going to put the records or the recordings of our meetings here. So if you miss a day or want to go back and review something, you can go watch it. Also, I did make a video of what I wanted to talk about on the end of last week and put that up here. I could make other videos on particular subjects that we don't get time to talk a lot about. Also, if there's a particular question or type of question that you guys would like some extra information about or extra help with, send me on an email or a message, and I can make a little video about it and post it here. So if you're looking for class videos, this is where I'll put them. So yeah, I really do, if there is something you'd like a little video on, do let me know. I'd be happy to make quick ones. I know a lot of you guys struggled a bit with the angular speed problems. I'm very happy to look at an angular speed problem today if you guys want to. But I do have a fairly sizable discussion on angular speed in this video if you want to check that out. I know angular speed can be a little bit weird. The formula is really straightforward. It's a little tiny formula, but translating the word problem into all those parts can be tough. So if you want to look at one of those, we can. A couple other things. I did, you guys using the forums well, and I noticed you guys were talking about those angular speed problems. So those are common ones to struggle with. But to help with that a bit, I did add a tool here to your homeworks. This message instructor button should have been there all along. If it wasn't, it should be in all of them now. If it's not on some problems, let me know. But if you hit this message instructor button, it sends me a message with a copy of or a link to the problem you're working on. So I can see what it is that you see. If you put in some answers, I can see what those are to try to help diagnose what happens. So instead of having to spend a lot of time trying to describe the problem you had, you can just spend that time talking about this is what you tried, this is what you're struggling with, and I can hopefully give a much more targeted answer. So that's nice for me, but when you guys are talking to each other on the discussion board, I added this new link to post the question on the discussion board. So you can just hit that and it will go to that week's discussion board. It should go to that week's discussion board. I tried to set them all up so they go to the proper week. If they ever don't go to the right week, just let me know and I'll fix it. But that way, also when you talk to each other on the discussion boards, you'll see that problem so you won't have to describe it. A lot of people were saying like 6.1, number 14, and it's tough because then you got to go find that 14. And a lot of people don't take that time to go search for it, or sometimes the numbers are different enough or the setup is different enough on the different versions of the problem that it doesn't translate well. So having that problem appear in the forums or in the discussion board is handy for you guys describing things and talking to each other. So hopefully that'll be useful for you guys and helpful. Any questions about either of those things? Or about the video links? Now we're happy about that. That's good. No, makes sense. Okay. But yeah, I want to reiterate if there's something that you want videos about, let me know. And if I'm just like looking in the discussion boards and see a lot of people go, these problems suck, I can throw out a quick video and see if that helps you guys, particularly on Fridays and Saturdays, because we won't be talking for a couple days, so that can be a nice way to keep that communication going. Oh, let's see, was there anything else on here? I'll talk about that later in the week. Oh, I did want to make note to you guys that the tutoring services are open and expanded. We do have the online tutoring that's been available. We also have the tutors now set up for Zoom conferencing. So you can do kind of a walk-in Zoom conference meetings with tutors. So there's a lot of different ways we're trying to make support available for you guys. And the more you can take advantage of that, the better off you'll be. So do keep that in mind and do try to take advantage of that. You know, the more help that you can get with those things, hopefully the happier all of us will be. So check that out, and do be sure to check out those videos in the video section. Okay. Let's see. Anything else about MyOpenMath or about any of that stuff that you guys want to look at or ask about before we dive into talking about mathy bits? Doesn't sound like it. I'll switch over to the mathy bits part, but if something comes up, let me know. So my question starting today is, do you guys want to talk a little bit about the linear speed, angular speed stuff before we jump into 6.2, or did you guys kind of work that out? Or was there anything else from 6.1 that you want to get kind of a final clarification for? If so, I'd be happy to spend some time chatting about it. Just let me know. Figured my issues out. If only all of us could figure our issues out. So that's good. Anybody else? Nick, good. Okay. Do watch that video on Angular versus linear speed. Part of the discussion there involves changing from radians per second to rotations per second or rotations per minute, and that dimensional analysis process in there can be helpful. And if you haven't done dimensional analysis for a while, it can be a little bit weird. So watch that, and if you need some help with those, let me know. I'm happy to talk about those a bit more or make some other examples about those. But you guys then started looking over into 6.2, and 6.2 brings up one of the really foundational tools this course will be talking about, and that's our 6 trigonometric functions. Our 6 trigonometric functions. Now, there are a number of ways of looking at, and even a couple of ways, different ways of defining these 6 trig functions. All of the definitions are essentially equivalent, though some of them are better at describing other aspects of these functions and of the geometry associated with them. We are going to start with the right triangle definitions of these functions, and then expand to the unit circle definitions and then the circular definitions over the next day or two. And you'll find that they really do kind of sit inside each other. So the right triangle definition, we're not going to lose that when we go to the circular definition. We're just going to expand from it. So the short version really is if I have a nice right triangle, again, this is our right triangle definition. So it's got a right angle in it. And we label one of those angles theta. Could be either one. We've got three sides here. We refer to the side that is on the far end of the triangle, the opposite side of the triangle, from the angle of reference. We call that the side opposite the angle. So if we were talking about this angle, that would be the opposite. The side of the right triangle that is up against the angle, that's adjacent to the angle, but is one of the legs, is our adjacent side. The two sides that make the right angle are called the legs of a right triangle. Oh, you still only see my open math. That's because I moved it to the other screen and didn't unpause it. Okay. Is that better? Better. Okay. So again, we're going with our right triangle definition for these 6 trig functions. If, by the way, if a bunch of things pop up on that chat and I don't see it because I'm looking at your wonderful faces, the couple of you who have wonderful faces there, or focusing on what I'm doing on the board, feel free to take your mute off and say, hey Matt, there's something over on the chat. So feel free to do that if I'm missing something, because there's a lot of information up here, frankly. So if somebody wants to kind of take on that job of kind of moderating that a bit, that would be helpful. So the famous side in a right triangle is, of course, the side opposite the right angle. That's got a special name. That's called the hypotenuse. And the other two are called the legs of the right triangle. And again, the one that's against the angle, the one that makes up the angle of reference, is the adjacent side. The leg that is on the opposite side of the triangle from the angle we're referencing is the opposite side. So if we were considering this angle instead, this would be the opposite and that would be the adjacent. So our 6 trig functions, what they do, what all of our trig functions do, I'm just going to use trig for the generic trig functions, their job is to take in an angle measurement. So we give the trig functions an angle measurement. And what it gives us back is a ratio of side lengths in a right triangle. So for example, if this angle was, say, 15 degrees, we should be able to tell the trig functions 15 degrees, and it would tell us what the ratios between particular side lengths are for this triangle. Which ratio depends on which of the trig functions we use. That is fundamentally what the trigonometric functions do. You give them an angle, and they give you a ratio. It's the first thing you want to get down about the trig functions. That is entirely what their job is. Give them an angle, they'll give you a ratio. Oh, jeez. Sorry, dog scared the crap out of me. Sorry if he scared you too. So the reason we have 6 trigonometric functions is because there are 6 possible ratios we can set up with those 3 sides. The first one is our sine function. We abbreviate the sine function SIN. All the trig functions have a 3-letter abbreviation. So the sine of that angle is one of those particular ratios. Which ratio? It is the opposite in ratio to the hypotenuse. So you take the opposite side of a triangle in ratio to its hypotenuse length, and that is the ratio that the sine function outputs. So, for example, if we had a right triangle out here and we had this angle, and say this side length was 5 and that hypotenuse length was 12, then actually, let me not make it 12 just to make my day easier, make it 13. Then the sine of that angle would be the ratio between the opposite and the hypotenuse. So it would be 5/13. And no matter what happened, if you took this triangle and scaled it, that's absolutely horrifying. If you took this triangle and scaled it way up, so it was much, much, much larger, as long as it is a right triangle, and these angles are the same, this side length might not be 5 anymore, but that ratio, if this angle is the same, that ratio is going to stay constant. So if this is, say, 10, that ratio has to be constant. So if this turns into a 10, that 13 had better turn into a 26. For a fixed angle, that sine ratio has to be the same. But that's just one of the possible ratios, the opposite side to the hypotenuse. We also have the cosine function. The cosine function, we abbreviate COS. Please don't say cos ever in your life. Don't say cosine, we just abbreviate it for writing it. And again, don't say sin, sine, cosine. It's a pet peeve. Hopefully you guys will start talking to me more, but when you do, we want to build good vocabulary and expressing habits in here. One of the unfortunate parts about online is because you guys tend to talk less. How you guys denote things and how you guys talk through things is often not as strong. So, I want to make sure we practice good habits. But the cosine function is similar to the sine function, but instead of being the ratio between the opposite and the hypotenuse, it's the ratio between the adjacent side and the hypotenuse of a right triangle. So up here, if this other side length was 12, then the cosine of that angle would be 12/13, the ratio between the adjacent side to the hypotenuse. And again, that is really all the sine and cosine function are supposed to do. You give them an angle in a right triangle, and they will tell you what that ratio is supposed to be. Here we're kind of saying, okay, if we know the sides, we can talk about the ratios. But the trig functions, you give it to the, say, 20 degrees here, and it will tell you what that ratio is supposed to be, and then you can scale it however you want. That's one of the ways that we'll use these functions. So that's 2 down. The next one, the tangent function. Again, abbreviated with 3 letters, T-A-N. Try not to say tan. Say tangent. Every once in a while I'll say tan. You guys are feel free to laugh at me. But should say tangent of theta. Tangent of theta, well, we have opposite to hypotenuse, we have adjacent to hypotenuse. Tangent is these other two, the opposite to adjacent. So the opposite side length in ratio to the adjacent side length. That's our tangent function. So again, for this example triangle up here, it would be the opposite. Opposite side is that 5 in ratio to the adjacent. It would be 5/12. Questions about those? I know we haven't done much with them, but we'll do a lot with them by the time we're done. But this is where we want to start. One of our first jobs is to get these associations down. We want to make sure we get the association. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. We want those 3 relationships down solid as fast as we can. There are even some mnemonics for it. One of the ones you'll hear a lot is SOHCAHTOA. Some of you are probably familiar with good old SOHCAHTOA. SOHCAHTOA, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. SOHCAHTOA. The first test in Math 112, about half of them, people write SOHCAHTOA on the top right when they get it. That's great. No problem with that at all. You want to make sure these relationships get down really solid as fast as we can. So, okay, that's 3. I said there are 6 of them. That's only 3 of them. And people often look at this stage and go, well, that's all of them put together. That we have these 2 together, these 2 together, and those 2 together. How are we going to come up with 3 more of these things? The trick is the other 3 are really the same relationships, just in reciprocal. Instead of having the opposite in ratio to the hypotenuse, we need a function that goes the other way, that has the hypotenuse in ratio to the opposite, and the hypotenuse in ratio to the adjacent, and the adjacent in relationship with the opposite. So the other 3 trig functions we often think of as the secondary trig functions, because these are the primary 3 that we will use. The other 3 are just reciprocals of these. So they are the cosecant. Yeah, let's start with that one. Yeah, I got to write it out. Actually, I don't want to start with the cosecant. I'm going to start down here, so careful where I'm writing that. But the secant function is really the most important of the secondary ones. So the secant function, abbreviated SEC, again, don't say sec. The secant function is the reciprocal of the cosine. So we're just going to flip those. It is the hypotenuse in ratio to the adjacent. The cosecant function is the reciprocal of sine. Cosecant CSC, the abbreviation for cosecant. I don't even know what you would say. But the cosecant function is that ratio between the hypotenuse and the opposite. And lastly, the cotangent is the last one, function, abbreviated COT, the cotangent function, reciprocal of tangent, adjacent over opposite. So generally what one does, I said we want to get these 3 down super solid, super fast. And we generally learn these other 3 in terms of their reciprocals. So we learn that cosecant is the reciprocal of sine, and remember it that way. That secant is the reciprocal of cosine, remember it that way. Cotangent, the reciprocal of tangent, remember it that way. Take a moment up here and, well, you're not up here, but take a moment and find the cosecant, the secant, and the cotangent for this triangle. I'll give you a minute to do that. Actually, while you're doing that, I'll be right back. Okay, so what did you guys get for the cosecant? We got silence, Matt. Are you guys being shy, or is there something I can help you guys with? Jasmine, 1315. My sound cut out, sorry. More 1315s. Okay, good. It's just that reciprocal of the sign. 13, I don't know why I said 15ths, 13/5. What about the secant? Good, 13/12. And following that pattern, the cotangent, 12/5. Nice. So given some side lengths, we can find all of those functions as soon as we get essentially these three memorized in these relationships. So any questions about that before we talk about it a little more? But anything you guys want to ask about that? Nope. All good. Good. I know you guys have been reading some of that and playing with that. But one of the things that often comes up is that, you know, these reciprocals often seem a little counterintuitive with the language. You've got, you know, all these reciprocals, but then you've got the co-language in here. Certainly, you know, apparent that we have sine and cosine, secant and cosecant, tangent and cotangent. And what that co-relationship is supposed to be telling us can often get a little lost in this, because it's certainly not the reciprocals. Because the reciprocals, other than the fact that every function's reciprocal goes from, you know, sine to cosine, well, sorry, from sine to cosecant, from cosine to secant, that it oscillates from a co-function to a non-co-function. Other than that, the relationship's not obvious. So I want to look at what it means to be a co-function before we move too far away from this. So got a nice right triangle here, legs of 3, 4, hypotenuse of 5. And I'm going to, just for consistency, still grab this angle down here, theta. So if we look at what the sine of theta is, and actually I want to find both the sine and cosine. Let's find all the primary three, sine, cosine, and tangent of that theta. It's just what we were doing up here. Sine would be the opposite over hypotenuse, so 3/5. Cosine, the adjacent over hypotenuse, so 4/5. And the tangent would be opposite over adjacent, so 3/4. Great. But what would happen if we change, instead of talking about this angle theta, to talking about this angle phi? Now, a couple of notes. In terms of degrees, just for simplicity, this is, of course, a 90-degree angle, if we're in degrees. And these two angles added together had better also add up to 90 degrees, because we know the sum of all three angles in a triangle, they all add up to 180. So if this is already a 90 degree, because it's a right triangle, these two have to add up to 90 just together. If we did the problem instead in radians, this would be a pi/2 angle, same as 90. And these two angles would have to add up to pi/2. So, we could say that those two angles have to add to pi/2. But often we will look at that phi, this other angle, as pi/2 minus theta. If this is equal to theta, then the other angle has to be 90 degrees minus theta, or in radians, pi/2 minus theta. Fair? I'm so used to saying fair, looking for shaking heads, but I only see one head. Well, the top of Nicholas's. You got shorter. So if we want to talk about this phi instead, if I wanted to find the sine of theta and compare that to the sine of, oops, I want those colors to match, sorry. Compare that to sorry, wrong tool. Compare that to the sine of phi and to the cosine of phi. Take a moment and find for yourself, make sure we're happy with this, what the sine of phi and the cosine of phi is according to these definitions. I'll give you 30 seconds. Okay, I don't know how long 30 seconds is. But sine should be opposite. Now, of course, because we changed angles, the opposite is now the one opposite that angle phi. So the sine should be that 4/5. And the cosine becomes that adjacent side now. What used to be the opposite is now the adjacent side, is 3/5. So hopefully you can see this connection. The sine of an angle is the cosine if we switch the angles. Cosine, if we switch the angles, turns into the sine. So this co-language has to have something to do with these two angles switching sides. Now, does anybody know or remember, we talked about it the other day, but remember what we call two angles that add together to be pi over 2? Or that add together to be a right angle? Shay, good, complementary. So these two angles are complementary. That's what that co is referring to. It is the complement function, or the complementary function. So the sine of theta is going to be equal to the complementary sine of the complementary angle. Or really, for any of the trig functions, again, I'll often use just trig as a generic for generic trig functions. The trig function of any angle is equal to the co-trig of its complement, pi over 2 minus that angle. So for example, and that's just written generically, but for example here, the sine of the angle is equal to the cosine of its complement. You can change from an angle to its complement by subtracting it from the right angle. These two were equal. Similarly, the cosine of an angle is equal to the complement of a complement, gets us back to sine of pi over 2 minus theta. So if we have this 3/4 down here, what other function is going to equal 3/4? Well, I don't want tangent. The cotangent of theta's complement, pi over 2 minus theta, is also going to be equal to 3/4. And of course, pi over 2 minus theta in this labeling we have here was the cotangent. So the cotangent of theta is equal to 3/4. Similarly, the secant of theta, here the secant is going to be, be careful, secant is the reciprocal of cosine. So the secant is going to be the reciprocal of this cosine, or 5/4. So the secant of that angle is 5/4. So the cosecant of phi, cosecant of the complement, should be that same 5/4. So that's what the co in all these co-functions means, what's representing. It's what happens when we switch from an angle to its complement. We switch from sine to cosine, from secant to cosecant, from tangent to cotangent. So that co-language isn't talking about reciprocals, obviously, because it didn't work here. What it's talking about is that jumping from one angle to the other. And when we go to our circular definitions, we'll see a little bit more of the geometric representation of that, of why it's important. But because I know you guys are going to be focusing on the language and wanting to know why that co, that's why that co. Guys, got any questions about that? We're going to have to talk about getting you guys to talk more, and or preferably show those faces more. It really does make a big difference being able to look out and see how you guys are looking and doing and get some feedback here. If not, you might as well just watch the videos. That's why we're here, right? The more you guys put in here, hopefully the more you'll get out of it. I know some of you are worried about the online, doing this class in only online being detrimental. We can compensate for some of that, or as much of that as we can, but only if you guys are involved in that interaction. So do, try to step up and be brave. The nice thing is, once people start doing that, once more people start doing that, then more people will be comfortable doing that, and it'll be easier and easier. And don't make me call Tom and tell him to pick on you, because I will. And you know who I'm talking to. Hi, Samuel. Hi, to it. So let's try one of these as just an example here. Let's say we've got a nice right triangle down here. Say this side length is 7 and this one is 10. And for this angle down here, we want to find the sine of that angle, the cosine of that angle. We're just going to find all 6 real quick. Now, I'm being fairly formal here, which I think is good at this stage, by putting these parentheses here. Again, these are functions, so this really is f of x. Just instead of the generic label f for a function, these functions have names telling us what they are. So think of this sine, cosine, tangent, cosecant, and so on as just the name of a function. It's f. Instead of our default variable being x, our default variable are these thetas. But this is the same notation as f of x. Function name, input variable. Function name, input variable. Usually when we have an f of x, it's a generic function, so we give some sort of definition for what it means. These functions are defined based on, well, we define them based on those ratios. So for our 6 trigonometric functions, take a moment and find the 6 values for this triangle. I'll give you a minute to do that. If you get stuck or have any questions, you can ask Samuel or Shay or Nick. Nick should know. Or Keegan. Keegan's pretty bright. Anybody feel like there's something missing? Shay, what's missing?
The bottom length.
The bottom length. I didn't give you that bottom length, but I seem to be expecting you to use it, right? It would be nice if only we knew some relationship between the legs of a right triangle and the hypotenuse. Do we know a relationship between those 2 legs and this hypotenuse? You'll find, by the way, that Keegan, good, see, I knew Keegan would know. The Pythagorean theorem that gives us this relationship, you'll find the answer, fundamentally, the answer to about 70% of the questions I'm going to ask you while we do anything in this course is going to be the Pythagorean theorem in one way or another. It really does govern a tremendous amount of how all of this is going to work because it governs right triangles. So since all of our work is so structured around right triangles, that relationship is going to be very fundamental. So the sum of the squares of the legs equals the square of the hypotenuse is going to be, for a right triangle, is going to be a very important relationship for us to be super, super comfortable with. Fair? So again, it doesn't matter which one of these are A, B, and C, as long as it's the two legs, their squares adding up to be the square of the hypotenuse. You can label them anything you want, but let's call that the 7 plus b squared equals 10 squared. So we're going to have to solve this for b equals. So take a moment and see what you get when you solve that for b. Good order, yeah. So everybody solve that for b and tell me what you get when you solve that equation for b. Type it out, I want to see it. I know you have to use a radical, you can just say SQU. About is okay too. We will tend to stick, Nick, with the decimal, we'll stick with exact values, but particularly for trying to communicate, on this thing, that's perfectly reasonable. Unfortunately, I haven't seen a right answer yet. I got a question mark. Keegan, question marks are good. No. Anybody else? Martin, you want to ensure what you got? Well, let's see what happens here. We get b squared equals 100 minus 49, right? So b squared is 51. So b is plus or minus the square root of 51. Is that plus or minus important? Absolutely. Now, in this particular application with a triangle, when we're in our right triangle definition, yes, we will use the positive length. So particularly if I had asked what length do we get there, square root of 51 would have been correct. But what do we get when we solve this? We get plus or minus the square root of 51. And as soon as we bust out of triangles and start using that circular definition, those negative lengths, those negative distances will become absolutely important, full on necessary. So if we are in the habit of kind of playing a little fast and loose with that plus or minus, we're going to get in trouble really fast. So certainly, you're not wrong. This length of the triangle will certainly be the square root of 51. But I want you guys to get in the super, super strong habit of when you solve, you formally have that plus or minus. And we go through the process of thinking, in this situation, do we need the plus or the minus or both? In this situation, we only need the positive version because we're talking about a raw length. Fine. But many situations we will want the negative, many situations we'll want to consider both. Fair? So super, super, super careful about that. I will harass you about that endlessly because well, it's fun and I care. So given that we then turn that into, or we choose the positive version for our triangle, then we should be able to bust these out. Fair? So real quick, because I know you guys have to go, we'll have what, the square root of 51 over 10. We'll have, what? That's what I get for trying to be real quick, right? You guys all panicked. How about 7 over 10? The square root of 51 over 10. See, it's nice to be able to see some of the faces go, what? It's really helpful for me. The tangent would be 7 over the square root of 51, which of course you would rationalize into 7 square root of 51 over 51. If you need a refresher on rationalizing fractions, do Google that or send me an email. I can make you a video. We do want to rationalize our fractions. Not doing so is just rude, so we don't do it. Cosecant's the reciprocal of sine, so 10/7 secant 10 over the square root of 51, which again will rationalize 10 square root of 51 over 51. And then cotangent's the reciprocal of tangent, so we could flip this back over and re-rationalize it, or frankly, just use this is better, square root of 51 over 7. Cool? Okay, so we want to play with those. Most of 6-2 is just getting used to this and playing a little bit with the calculator to get some actual values for angles. We'll play with a little bit of that tomorrow. I will move that 6-1 back a couple days because I did want to talk about 6-2 on Thursday, but we had our technical difficulties. So any questions about any of that? You guys happy so far? Yay. Yay. Do let me know if anything comes up. And until then, I'll see you tomorrow. Feel free to let me know if you need anything, and have a wonderful day. Thank you, Samuel. Anything you guys need? Dominic, you're good? All right. Then I'll see you tomorrow.